All right, guys, hi. Today we're doing 1.3 and ideal geometry. So you'll notice your homework is on page 13. It's numbers 1 through 37 odd. Okay, so today, talking about an ideal geometry, we're really just talking about geometry. Like geometry is more of a logic class than a math class even, because you have to we're working on figuring out how mathematicians think, how they process, how they prove things, how they they draw conclusions. Okay, so kind of thinking about deductive and inductive reasoning kind of things. So we're just talking about this ideal geometry today. Our objectives are to describe the structure and characteristics of an ideal geometric system, and we're going to state and apply some key postulates and theorems to get us started. We're going to learn new postulates for the first couple of chapters, and then, well, maybe it's just sections actually, and then we're going to start learning theorems. Like every lesson there'll be a new theorem for like 3/4 of the year. I will give you a reference sheet to help you with those so you can look back and use them. So you wouldn't necessarily have to memorize them, but you have to know them well enough to be able to use them. That's going to be the tricky part. Okay, so let's get started. The Greek mathematician Euclid was the first one to organize the known geometric properties and principles into a geometry. All right, this says a geometry because there's actually more than one study of geometry. There are different geometries. We do study Euclidean geometry. It's the most popular, but there are other geometries out there. And then a geometry, then, is an orderly, systematic body of math knowledge. All right, so Euclid is considered the father of geometry, and Euclidean geometry is still used today. Again, that's what we study is Euclidean geometry. All right, so postulates, or axioms, you might hear, are basic relationships that are assumed true without proof. Okay, these are the basis for our theorems. So we're going to learn some of those today. And then our theorems are statements that are shown to be true. So postulates are assumed true. Theorems are shown to be true by a proof. Okay, this is a logical progression of reasoning. It's kind of like a treasure map. Okay, or if you have this piece of information and then now you have like what information can you get from that piece of information, and just going through. So a proof of a theorem, so because we're going to do proofs this year, so proof of a theorem can use definitions, it can use postulates, and it can use previously proven theorems. So we can use other theorems to prove a new theorem true. Okay, so that might sound like a lot that you don't understand. That's okay. We're going to make it make more sense as we continue to progress. All right, so mathematicians look at 3 characteristics in a set of postulates, okay, when evaluating a particular geometry, okay, because again, there's more than one. So its basic assumptions should be that it's consistent, the 3 characteristics, independent, and complete. All right. So for the first one there, consistent. A postulate system is consistent if its postulates do not contradict one another. So let's look at example 1. Okay, it says determine whether the set of postulates is consistent. So postulate 1, if 2 lines intersect, then every other line in the plane intersects one of them. Postulate 2, if 2 lines intersect, then there is exactly 1 line parallel to both. So are these consistent? So consistent means they do not contradict one another. So the question is, do these contradict each other? Yeah, okay, because postulate 1 says if 2 lines intersect, they both start off the same way, right? If 2 lines intersect. The first one says every other line in the plane intersects one of them. So if we have a line, so every other line in the plane intersects one of them. Okay, so that's saying that every line in the plane must intersect one of the two lines. However, in postulate 2, it says there is exactly one line parallel to both. So postulate 2 requires that a line be parallel to both without intersecting either one. So this one is not possible. They're contradictory, or they contradict each other. Okay, you can't have lines that are parallel and perpendicular, or intersecting. Not perpendicular, pardon me. So you can't have lines that are parallel and intersecting. So this would say, so the answer to this question, it says determine whether the postulate is consistent. This is not consistent. Okay, or these postulates are not consistent. So that means that this geometry that had those two postulates would not be consistent. It would not be a good geometry system. Okay, let's look at number 2. Independent, okay, is the next one. A postulate system is independent if no postulate can be deduced or proved from other postulates in the system. Therefore, every postulate is necessary. Okay, so every postulate is necessary. Okay, they're all individual. So, example 2, determine whether the set of postulates is independent. Postulate 1, if an animal is named Polly, then it is a parakeet. So we've got some if-then statements. Postulate 2, if an animal is a parakeet, then it is a bird. Okay. Postulate 3, if an animal is Polly, then it is a bird. Okay, so we're looking to see if it's independent. Okay, independent means no postulate can be deduced or proved from other postulates. Each one is necessary. So here's the thing. Postulate 3, if an animal is Polly, then it is a bird, is a logical conclusion of 1 and 2, right? 1 and 2 says if it's an animal is named Polly, right? So it says, okay, if an animal is named Polly, then it's a parakeet. If it's a parakeet, then it's a bird. Postulate 3 is saying if an animal is Polly, then it's a bird. Well, we don't need that postulate. We already know that from postulate 1 and 2. Okay, so that's just the logical conclusion. So that would mean that this one is not independent. Okay, it's not independent. And you could put because, so B/C. P3, postulate 3, is just a logical conclusion. Of postulate 1 and postulate 2. Feel free to use those abbreviations as long as you know what they mean. So you might want to put POST for postulate 1 and POST 2. Just make sure you know what your notes mean. All right, let's clear this up and look at 3. So the third part is complete. A postulate system is complete if it forms a sufficient base for a full description. So every statement expressed within the system can be proved or disproved from the postulates. So here's an excerpt from your book, which I really love, right? An ideal geometry would have postulates that are consistent, independent, and complete. However, Kurt Gödel's incompleteness theorems that were proved in 1931 show that such an ideal postulate system is not possible. Okay, that's kind of wicked to think about. So we're studying a geometry that's actually not ideal. Okay, it's not perfect. So our limited and fallen reasoning is not capable of adequately describing God's wonderfully created universe, which we see this every day with things that happen and we don't understand, right? Like we just don't understand God's knowledge and how he does things. So because of that, our mathematical systems cannot be complete. I mean, that's why we have things like infinity. We don't know where numbers ever end, right? We know that there's eternity. We can't wrap our heads around this idea of infinite numbers and a number that goes on forever and doesn't terminate. It's wicked cool, right? So our mathematical systems cannot be complete since we will never know everything about geometry or any other subject for that matter. We'll never know everything about it. So every useful postulate system in mathematics is consistent, and some are independent, but none of them are complete. Okay, so that's helpful to know. So every useful postulate system is consistent, some are independent, that's where our goal, and none, absolutely none of them are complete. It is impossible. The only entity that has a complete and postulate system is the Lord above. It's pretty awesome to think about. So, all right, wrap your head around that one for a little bit while we clear it and go on to the back. All right, so on the back, we just have some things that are listed here for you with some examples. So our first postulates that we're going to learn are called incidence postulates. Okay, so the first one is an expansion postulate. Okay, it says a line contains at least 2 points. A plane contains at least 3 non-collinear points, and space contains at least 4 non-coplanar points. All right, so we need to break some of these down. So a line has at least 2 points. So we have this line here. It's line K. Okay, we can see that it's named. Has point A and point B on it. Okay, a plane says it contains at least 3 non-collinear points. Okay, so to be a plane, it has to have another point. So point C here, that's not on the line. It's non-collinear. Okay, so non means not, co means on the same, right? On the same line. And that's what makes our plane. And then it says space contains at least 4 non-coplanar points. So we have to have a point that's not even on the same plane. A, B, and C are on the same plane. D is up above it. Okay, so like you have to think about 3 dimensionals. So it's like you have a sheet of paper laying on your table for your plane, and D is something above that. Okay, so that's our expansion postulate, and that gets us a line, a plane, and space. All right, a line postulate. Any 2 points in space, okay, any 2 points in space lie in exactly one line. So any 2 points can make exactly one line. That's all that's saying. The plane postulate. 3 non-collinear points. Okay, so 3 points that are not on the same line lie in exactly one plane. So they can make, right, we would get different lines out of these. We could have line AB, pardon me. We could have line AC. We could have line BC. But the thing is, all 3 of those points, my eraser's not going here. I was gonna erase. I'm flashing. So, but what this is saying is 3 non-collinear points, so 3 points not on the same line, lie in exactly one plane. It might be flat, or it might be horizontal plane, it might be a vertical plane, it might be a transversal, like diagonal, either way. Okay, then we have a flat plane postulate. If 2 points lie in a plane, then the line containing those 2 points lies in the same plane. Okay, so all it's saying is that this plane that contains these 2 points is in the same plane. I mean, like they lie in the same plane. The line and the points are in the same plane. Well, it's like, well, duh. Okay, that's the thing about postulates and some theorems, but postulates especially, you're like, well, duh. I know this. Like, you don't have to explain this to me. But that's what geometry is about. It explains everything. All right, so the next one, line intersection postulate. If 2 lines intersect, then their intersection is exactly 1 point. Okay, so they intersect, 2 lines intersect at exactly 1 point. Okay, I'm going to erase these and I'm going to slide up to our plane. Okay, so our plane intersection postulate says if 2 planes intersect, okay, then their intersection is exactly 1 line. Okay, and that's what this line is here. It's showing where those 2 planes would intersect. So think about, like, if you crossed 2 pieces of paper, or you, I was trying to think, like when you do, when you put maybe a piece of glass or something into a bowl of water, like, and they cross, like that's a little tougher because then you have a whole plane where the water's touching. So maybe not the best example. But if you can cross 2 pieces of paper, they're going to cross in a line. Okay. Video gamers might pick up on that a lot easier. Okay, so from these postulates, we can get some theorems. Okay, so we have 3 theorems this section. So theorem 1.3.1. So these theorems are named in order. Okay, so the way that they're named is the first 2 numbers are the section that they show up in the book. So these are both coming from section 1.3. And the last number is the number that the order in which they appear. So this is the first theorem in section 1.3. The next one is the second theorem in 1.3. And then we have the third theorem in section 1.3. All right, so theorem 1.3.1, a line and a point not on that line are contained in one and only one plane. So a line and a point not on that line, so non-collinear, are contained in one and only one plane. Okay, so we're using those postulates to come up with this. And so then the proof is here. Okay, this is your first look. This is called a paragraph proof, and it goes through and it tells you why that's the case. So given a line K, okay, which we have, and a point C, that's down here, not on the line, the expansion postulate, it tells us where to look, states that the line contains at least 2 points, which can be called A and B, so we could label those A and B. Okay, because A, B, and C are non-collinear, exactly 1 plane passes through these 3 points. And it says, hey, that's the plane postulate. It's telling us how to do that. So this is a proof. It's walking us through. Okay, so since A and B are both in this plane, the flat plane postulate guarantees that line K also lies in this plane. Therefore, exactly 1 plane passes through a line and a point on that line. Okay. So sorry for the hiccup there. There was a glitch in my recording that I had to get fixed. So if everything didn't quite line up there, I apologize for that. Then let's look at the next 2 theorems. So theorem 1.3.2 says two intersecting lines are contained in one and only one plane. So two intersecting lines are contained in one and only one plane. All right, theorem 1.3.3 says two parallel lines are contained in one and only one plane as well. All right, so you guys are free to get started on your homework.